Hello, everyone, and thank you for attending today's webinar, Understanding and Optimizing EBSD Camera Settings. Before we begin, I would like to cover a few housekeeping items. At the bottom of your audience console are several application widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget at the bottom and submit your question. I will try to answer these questions during the webcast, but if a fuller answer is needed or we run out of time, you will receive an answer by email. But we do capture all questions. A copy of today's slide deck and some links to additional materials are available in the resource list widget, which looks like a green folder. You can expand your slide area by clicking on the maximize icon on the top right or by dragging the bottom right corner of the slide area. If you have any technical difficulty, please click on the help widget. It has a question mark icon and covers common technical issues. On-demand version of the webcast will be available approximately 1 day after the webcast and can be accessed using the same audience link that sent you here earlier. So now I'd like to introduce myself. I'm Sean Wallace here at EDX in Mahwah, New Jersey. I'm the EBSD applications engineer. It's my job basically to help you guys get the most out of your system, understand what's going on, and then ultimately in the end get you good quality data to help you solve your questions. So at this time, we'll start the presentation. The whole reason I chose this topic to do is because I often go on customer sites and I can see them using their system, and I see that there is a little bit of lack of knowledge of how to essentially get the data they want while getting it optimized. So getting it at the speed they need and at the quality they need. And those two things are kind of a big back and forth battle between your data quality and your data acquisition time. That's what we're going to talk about here today. So a little bit about just EBSD detector geometry to make sure we're all on the same page. I have a feeling for most of you guys, you understand this. Here's our detector geometry. And we can see that, of course, we have our specimen tilted to 70 degrees, basically so that we're projecting towards our phosphor screen. The pattern is then recorded by the detector, and these bands that you see are going to represent the reflecting lattice planes of the diffracting crystal volume. So basically, your crystal structure is shown by the bands. Again, this is probably old hat to most of the people in this room. Again, the tilt's pretty important, and of course, the geometry in general. And here are our two detectors. We can see that we've had two models of detectors. Most of you probably have a DigiView or the Hikari Super, with the DigiView being our slower speed camera, but a max of a higher resolution, giving you a higher quality pattern, while of course the Hikari model is quicker, but at the cost of lowering your resolution a little bit. And the speed difference between the two cameras can be pretty strong. If you're using a DigiView, you can often run 160 to 200, depending what you're doing. With the Hikari Super, you can collect large maps really, really quickly. So at this time, we're actually going to start off and ask you a relatively basic question just to get an idea of what system you guys have. And here's a poll for you guys. So the question is what EBSD camera do you have? So we've included both ours and our competitors because we want to know essentially what you're working with. My understanding is that most of our customer base and probably most of the people here have Hikaris. And the Hikaris are the same technology essentially as the DigiView. It's just, again, the resolution and how fast you can pull that data off. We're getting quite a few responses relatively quickly. I'll go ahead and give you guys another minute. As of right now, what I'm seeing is kind of what I expect. Most people here tend to have the Hikari system, quite a few with the DigiView, and then a couple on here with our competitors' brands. Also, there is a relatively large percentage on here right now, about 15, that does not have a camera. I'll go ahead and show you guys the results so that you guys can see what we have going on here. So again, this is kind of what I expected. Decent amount of Hikaris and DigiViews, and of course don't have. It's always good to see people interested in the technique and figuring out how the cameras work. So I'm going to be talking a lot about different settings on our cameras. And the biggest question that I sometimes get is, of course, where do I see these? So there's two spots where you can see the advanced settings on your camera. One is going to be in the green bar on the top of Team. It's going to be underneath the advanced. Or you can also bring out the pull-out menu on the right and do the EBSD camera. These advanced settings menus contain all of the information that we need to better understand what our camera is actually physically doing. There's the optimize button, which basically optimizes the camera automatically for you. There's the gain and the exposure. These are going to be our two big things that we're talking about today, gain, exposure, and also binning. These all work together, interact with each other to essentially get the picture off of the camera at a speed and quality that you need for your data. And that's going to be the big thing here, and what I'll be talking about is what kind of quality of patterns do you really need for the camera to consistently index your material. So we can actually see a pattern here, and this is the textbook pattern. You can see it up in the EBSD camera window. That's overkill, and I'm going to talk about that. We'll talk a little bit about the analytical beam current and what's going on here. We've done an informal survey in the past of SEM and EDS suppliers, and essentially we found that most people work from like 1 to 100 nanoamps. That's the general broad range of going on. The Hikari camera was designed to operate about 100 picoamps to 10 nanoamps. Again, if you start getting higher than that or lower than that, it's not a bad thing, but it's not what it was designed for. Then the results shown here are usually obtained at 5 nanoamps or less. We don't have high beam current machines usually on site. Most people don't have access to them, so we try to keep it in a normal range. And the other thing to realize is that extremely high beam currents are not required for high-speed collection of high-quality data. You can use it as kind of like a crutch to get there if you need to. If you start throwing more electrons around, you have more electrons coming off, but you don't always need that. So with that in mind here is what is my ultimate goal of this whole thing here? And it's to kind of show you, again, how these settings run off of each other and what you need. So the first time I'm always collecting data, the first question I ask is, what is the purpose of the data I am collecting? Do I need high resolution work for high resolution EBSD work, or am I just looking at general grain statistics, maybe a grain boundaries or grain size or orientations? I always need to start basically asking myself, what is the question that I'm looking to answer from this data set? And with that in mind, it really kind of leads to the next level question of what quality of the pattern do I need to achieve my goal? Again, if I'm doing that high resolution work, well, I need high resolution patterns. I need to slow my camera down. We'll talk about this. The binning needs to be relatively low. I need to make sure that I have good, crisp patterns to do my work. If I'm not doing that kind of work, and I'm working more, again, on like grain statistics things, I don't need that high quality patterns. I can still find my grain boundaries. I'm still getting good orientation data. That's what I need. But the question that I'm really asking myself is how well and accurate can the Hough transform find my lines of my patterns? I'm looking, that's the ultimate goal here. The patterns that I'm getting, that I'm seeing, are not what the computer's seeing. And this is kind of the big disconnect between the human brain and how the computer thinks. The Hough is how the computer finds the lines. And with that comes our next question. So how well do you understand the concept of the Hough transform? Again, the Hough really is the brains behind what's going on when we're actually dealing with our system. So our responses here is going to be, what is that? Again, you've never heard of it. The other one is going to be, basically understand enough to know what it does, saying, I understand it to a level that, again, I understand what it's doing, and that's good enough. Or, the rare person who, again, stares at their ceiling tiles at night and goes, hey, let me just transform this into Hough space in my mind, and then, of course, that'll put me to sleep. So I would say that I would put myself in the category of between the two. I understand it enough in staring at my ceiling tiles. The Hough transform in general is not an easy concept to understand because of what it's doing and how it's bouncing back and forth. So here's our answers, and again, it's pretty much what I expected. We're looking at, what is that? I'm going to talk a little bit about it, but I'm not going to go into it in depth because, again, it's a very difficult concept, and while you need to understand the basics of it, you don't need to understand much beyond that. Understanding it to know what it does is really half of the battle, and that's where most of people here are learning and figuring out what this is. So if you understand enough to know what it is, you're good enough. And of course, there are people who, again, can do this in their mind and say, okay, let me transform this as I go on. So here is basically what the Hough does. Here's a diagram of a pattern. In the middle is the Hough transform itself in Hough space. And there on the right is basically the Hough putting the lines back on. Again, the Hough is a way for the computer to find lines. You have to remember that a computer looks at problems differently than you do. You can look at that, you can see lines, you can draw them on. A computer, it's not that easy for, and that's kind of that's what the Hough does. So the way the Hough works is essentially it starts pulling the data out at basically the pixel level. It says that for a given pixel in an image could belong to an infinite set of lines. And I can pull this into what's called row theta space and start looking at it. And essentially what I'm doing is looking at, what is that pixel strength at each one of these points. And I can do this is I can keep making a whole bunch of essentially sinusoidal curves over and over and over again using the equation you guys see there. Again, the specifics of the Hough are not that important to know. It's a general concept that what's going to happen in the Hough space is that essentially what you see as a line for the computer is now going to be transform it into a point. So here's an example where I have a line. I have 4 different pixels on this line. And if I do this Hough transform, each one of these pixels essentially turns itself into a sinusoidal curve. And because they're on a line, each sinusoidal curve is going to essentially interact and intersect at a point in the Hough space. And we can see that there on the right. We can see where, again, all these lines come together. And if you look on the Hough space, you're going to see basically a pattern, dark, light, and dark. This is what the computer is actually looking for, is basically dark, light, and dark. And that's when the computer's going to say, okay, I found a line. But you can see that in this case, there are multiple Hough peaks off of that line. So again, this is just doing the entire image. You'll get more than one Hough peak. Here's just kind of another version of that. You can see that if I do one line, I'm going to have them all converging at one point, and also have the curves traveling off inside of that. And again, if I do this for each line / pixel in my image, I'm going to have multiple Hough peaks. So this is the accumulator array. It's basically just doing this for the entirety, not just for 4 points. And again, I can do this for the entire thing. It's not that important, again, to understand what's exactly going on. It's important that a line, here, like on the left side, will turn in to what we call a butterfly, essentially, and to a very, very bright spot with 2 dark spots around it. That's the key for the Hough. Now, the thing is, and kind of what I try to show people in general on their machines, is that the Hough is extremely, extremely powerful. And I'm kind of giving you guys a little bit of homework here, is how to is take a data and start pulling it apart and start getting these parameters I'm talking about today, start playing with them and seeing that the Hough can consistently get good, consistent data off of relatively poor patterns. And this is what the next slide is going to show. So in this case here, we have a pattern on the left. This is going to be a high quality pattern. The pattern in the middle is a lower quality pattern with higher bidding, where we started to grade our pattern quality to gain speed. Now on the right here is the final map for our middle data set. What I can hope you can see here is that while it looks basically uglier, it's kind of fuzzy, the Hough doesn't care. And still provide accurate results for the final map. So this is everybody wants these beautiful, crisp, clear patterns, but you don't need them for your end product. And that's important to understand, especially when you're gaining speed. You're never going to have a nice clear pattern like on the left if we're trying to really, really push our camera to its limits. So with that, let's start talking about our camera signal. This right here is our camera signal level. This is what you see when you're looking up on the right side. What you're going to be looking for is what we have in the middle, which is our optimal camera signal. This is going to be what you're aiming for. On the left, we have an undersaturated image, which basically means I'm not getting enough signal to my camera to get a good, consistent, high-ish quality pattern that I need. And on the right, we have oversaturated camera. Your goal, essentially, when we're doing this, is to have what we call a 0.85 saturation index. The saturation index is listed underneath your camera, and you can see it changes as you change your camera settings. So I can start using my gain and my exposure to start getting these to the level that I need. The reason we choose 0.85 is because that different parts of your samples are going to have different diffraction intensities or strengths. And if you optimize your camera in an area that has a lower level and move the camera to a higher level, you can oversaturate your image. And that's what we're trying to avoid by keeping it down to the 0.85 instead of 1. Because 1 would be what we really want, but again, your sample isn't uniform enough usually for that to happen. So the biggest thing here is that when we're doing this, something called binning is going to be our biggest kind of, our biggest advantage of gaining speed. Because of what I'm doing with binning is I'm effectively making it more sensitive to light to increase my frame rates, but I'm losing a little bit of resolution in my patterns. So in this case here, let's say I had a detector that was 1024 by 1024. I have quite a few pixels. I'm getting a high resolution image because of each pixel I'm getting, just the light from that area. When we do something called binning, I'm grouping a group of pixels together to essentially increase my sensitivity to light. But when I'm doing that, I'm losing essentially the spatial resolution of the pattern. Now, in this case here, we can see that I've gone from 1 by 1 to 2 by 2, and even down to 4 by 4. And you can see that there's a decent change in the level of the actual camera itself. You can see the patterns just changing as we do this. Now, again, the issue here is that you lose this pattern, but you're starting to gain speed, and the speed gains goes up really, really, really quick. So I have a question real quick that I see here. It says, does 1 pixel mean the camera is basically full saturated? And the answer to that is yes. The camera essentially looks for the brightest pixel when it's doing that. But that means that there's usually areas very, very close to that, and that's why we choose 0.85. I also have another question here saying, where do we enter 0.85? The 0.85 is not a number that you enter. It is a number that you're aiming for. So the number will change as you change your slider bars. So if I had a saturation sitting there at about 0.5 and I increase my gain, my saturation is going to start gaining with it. And with that saturation gain, that's what I'm aiming for. I'm aiming for 0.85. I can't just set it. It would be nice, but I can't do that. So again, this is what I'm aiming for through these settings. That's my goal point, is 0.85. It's not something I can just put in. So go ahead and look at the effects of these camera settings. We can see here different patterns with different binnings. So at 1 by 1 binning, you're looking at about 2 seconds per pattern. Again, this is not something you would normally run a map at. 2 by 2 binning takes about half a second to get a pattern. 4 by 4 binning, you can see we're down about 0.13 seconds. And all the way going down to about 10 by 10 binning, you get down to about 0.03 seconds per pattern. This is what we're starting to see is a massive gain in speed by playing with the binning. What also you can see here is the pattern quality. While we're starting to get a little bit fuzzier, the machine doesn't care. The Hough doesn't care, and that's our ultimate goal here. Remember, we're not, when we're doing this, we're not there to make pretty pictures for your eye. We're looking at making a picture that the computer can interpret and get the orientation off of. Now, of course, if I'm doing like publication quality work, I don't want to sit there and and understand, what's going on. It's just, if I'm doing publications, I want a good pattern to show my work, excuse me. And that's what you can go ahead and take a good pattern and pull it out and do that. So that's kind of, again, you can sometimes take these patterns and use them, but for doing a map, I don't want that. So when I'm doing a map, I'm usually doing at least 4 by 4. Sometimes I'm doing 8 by 8 if I'm getting good patterns. And I can start pushing that even higher if I need to. And here's basic frame rates we can see when dealing with different binnings, 100 by 20 pixels. But again, what we're seeing here is that our camera starts going up really, really quick. And with a Hikari system, these values are going to be even higher. So you can really, really start pushing it. And often I can take maps at, 800 to 1200 patterns per second and really start pushing the speed that I can do a map just to get the data off and push it off. Here's the camera settings. Here's the binning levels we have. And we can see that there's quite a few on here. We can see that there's going to be differences here because the CCD chips are actually different between the DigiView and the Hikari. But we can see in general that there's relatively, there's a big change between these two because of that. Again, when I'm doing mapping, when I'm doing high-speed mapping, when I'm starting to push my camera to my speeds, I will usually be running at about 10 by 10. And we can see that the 139 by 104 pixels for the DigiView, essentially the Hikari is about half that at 64 by 48. That's a relatively big change in your pixel resolution, but the Hikari is sensitive enough to really start pushing speeds to be able to push and get higher quality, or not higher quality patterns, but patterns that are good enough at high speed. So this is going to be your real thing you're looking for here is understanding that when I start playing with these settings, especially things like binning, the Hough just still finds our lines. Remember that the Hough is looking for basically dark, light, dark. And when I start playing with my binning, what will happen is that you can see my difference on my left side at my 120 by 120 versus my 60 by 60 is that it starts to get a little bit elongated. But, there is this relationship here, but the Hough doesn't really care all that much. And a little bit of a change in the Hough doesn't really change the orientation of the lines themselves. So when you're doing this and you're actually working through and lowering your binning, you're still getting consistent orientations from your data that's coming through the Hough. So if I put 120, this picture on the left end, and indexed a pattern based on that, I would get something very, very close to the 60 by 60. And this is where we need to start thinking about the actual patterns themselves, looking at what's my end goal. Again, if I really, really need that precision for my orientation, to like half a degree, then I need to start thinking about binning like at a 120 level. If I'm really just worried again about grain statistics, I can go ahead and push it to the 60 by 60. So this is what I'm starting to think about. This is what's my end goal, and my end goal is going to be the thing that's really kind of pushing what's going on. So a question just came through asking if these patterns are from the Hikari or DigiView. Most of these ones today are going to be from the DigiView camera. Again, they just tend to show better, but in general, the Hikari is going to give you the same quality of pattern for most of these things. That's good enough for what we do. The DigiView is our high-resolution camera. It just gives you usually better patterns, but again, the Hough here is the key. If you notice in most of this stuff, I'm not talking about frame rates as much because there's a big difference in frame rates between the DigiView and the Hikari. The question is how much can we push basically to getting 100% of the speed out of our camera that we have, and that's the same process between each camera. So there's basically the patterns in the Hough. The other thing that will also can affect your speed is going to be a little bit of the Hough settings themselves. And one of those settings is called the Hough theta step. So I actually didn't cover this, but you can go to the Hough transform inside of your inside of the pull down menus on the right side, and you can change the theta step from 0.5 to 3 degrees. When you're doing this, when you're doing this kind of work, you're changing this binning. This binning is going to increase basically increase or decrease the computational time. If I go down to 0.51 Hough, the theta step, excuse me. This means that, I'm essentially adding a lot of computational time, while at the 3 degrees, I'm basically lowering the amount of pixels I have to cover in Hough space, which means that I can move on quicker. Basically, I can take my pattern, do my computational work, and go on. So this is what the Hough does. I have another question of basically what does 120 by 120 binning represent? In this previous slide, this is just the actual binning of the pattern itself. It's the pixel length of this one. So this one over on top here, this left side, is 120 by 120 pixels. This other one is 60 by 60. And also remember that 120 by 120 versus 60 by 60 is a very large difference in the amount of overall pixels in the setting. Because when you're binning together pixels, if you bin together something like 2 by 2, that's 4 pixels. If I go bin together 4 by 4, that's a total of 16 pixels being put together. And that's a big, big difference. Something to keep in mind. Another question that just came through that I should answer now is, can you reprocess the Hough with smaller theta step from a saved raw pattern? And the answer to that is yes. Anytime if you save a pattern, you can go back and redo it, as long as you have the raw pattern. Again, if you just save the Hough, you're kind of out of luck. Actually, I think even if you save the Hough, you should be able to do that now that I think about it. But if you have the raw pattern, you can definitely redo the Hough with a smaller theta step. Now let's start talking a little bit about gain. Gain is going to be kind of the workhorse of really, really pushing what I'm doing. So what gain does is increases the noise that your camera picks up. So what we're doing now is we're lowering our signal a little bit and gaining noise. So essentially our camera is getting a little bit less, it's getting less sensitive to our actual signal, but we're getting enough that we can push off a frame, save that frame, and index it. So here's an example. On the left, we have, this is probably a silicon pattern we can see. We have a 0% gain, nice crisp pattern. And as I add gain, you can see that my pattern gets fuzzier. This is going to allow me to make a tremendous increase in the speed that my camera can push basically a frame off of it to save the data. Now, this here is, again, this is going to be your main thing. The question I also just got in is, why is the upper half less focused? This is usually a positioning issue with the, or not a positioning issue, but it's because of where the pattern center is itself. If you are looking at the pattern center is usually towards the upper part of the image, but it changes with the geometry of what scope we're dealing with. In this case, we're probably dealing with a system that had the pattern center more towards the middle or maybe even towards the bottom. This is just a scope geometry issue. So now that we have this gain, let's go ahead and talk a little bit about also the microscope conditions. So there's only a couple different microscope conditions that matter for the actual data collection. And honestly, one of those is going to be beam current. So if my beam current goes up, I'm essentially throwing more electrons at my sample. I'm also getting more electrons off of my sample that are diffracting towards my pattern itself. Now, when I do this kind of thing, I'm basically just giving myself more to work with. So on the example on my left, I have a 0.6 nanoamp beam current, and it takes me about 4.6 seconds to get a good picture. This is kind of overkill. I wouldn't really usually collect a pattern in 4.5 seconds. On the right, we can see that I've essentially taken my beam current up by an order of magnitude, and my time now has dropped to 0.6. Again, this pattern right here is very strong pattern. I can start playing again with my gain and my binning to basically weaken that pattern quality to start, again, giving myself more wiggle room to increase my camera speed. So now that I have this setting here, again, let's go back to gain real quick and see what we can do. So with minimum gain, I can get 2.7 seconds all the way up to 0.15. Again, remember, our main goal on this is always to try to have that saturation index around 0.85. So we can see now that we're starting to look at all these different factors coming in at the same time. I have my exposure time, basically how long my camera is taking a picture for. I have my gain, how much noise I'm adding to it. Then I have some of these scope conditions, like my current, right? These are all things that are now starting to play in to me pushing that speed quicker and quicker and quicker. So at this point, I'm essentially set up to see how these things are interacting. And that right there is really kind of the key to this, is this interaction. Okay, do I want faster speed? Increase my beam current. Do I want higher quality pattern? Okay, maybe I'll start increasing my exposure time, lowering my gain to make sure that my pattern is not noisy. These are all of these kind of goals are what I'm aiming for. I'm aiming to get the pattern that I need for the data that I need. And again, that's always kind of our big goal here is what kind of data do I need for the stuff I'm looking at. So this right here is an example of starting to play with this gain to look at what I'm looking at. And here again, we can see this huge difference in our frames per second based on looking at our gain. So here we have a nice pattern here with a zero gain, a signal to noise ratio of 1.9, and we can see again a nice close pattern, but I'm running about 45 frames per second. So I was taking a large map. This would take a while. This data here is also, let me make this clear, this is from our Akari system. The easiest way to tell that is I have almost 800 frames per second, which I would not be able to get on a data view. So if I start pushing this, I start pushing my gain, we can see these large increases by doing this. And the thing I want you to see in this kind of data is look at the pattern quality difference between the top left and the bottom right. To our eye, there's a big difference. But our eye is not what's doing the work here. What's doing the work here is the Hough transform. And the Hough transform sees these essentially as the same quality of patterns. And because of that, I can go ahead and get this, order of magnitude difference between 45 frames. In this case, it's actually 40 times between these two, up to 800 frames to really start cranking out high quality maps at high speed. And I can even push that, to a high level. And here's basically the final example of this. Look at this pattern. Can you see lines on this pattern? You can see the basic zone axis here, but the secondary lines, go back to the previous slide. So we can see, as a human, we can see these lines on our gain 25 one, where we can see that these lines are something we can see. But in this case, these lines here, I can't see them as a human. So the human's not doing the work. The computer is, and the computer can get consistent data off of what we see as noisy patterns. So in this case here, while it's difficult for us to visually observe these EBSD patterns, the data was about 99% accurate. This right here is what we're looking for. The question I just got is, what I heard is the gain should not go over 2. No, the gain can go way up. The gain, what you want, you can push the gain up to about 25 or even 30. What you're really looking for is again, as long as you're getting good quality of patterns, you're okay. And this is your goal. Again, your goal is the data quality. Also, just got another question of about spot size. Spot size doesn't really change any of this. It's basically just your interaction volume, and your interaction volume will change a little bit with your beam conditions, but it doesn't matter for the Hough itself. So that's again not something to worry about. Going through some other questions real quick since we're here. If we can't visually confirm if the pattern is giving good quality results, how do I know if our parameter choices are good ones? Now, what I'm usually do when I'm looking at my camera settings is I'm not going to start off with a map. I'm going to start off with what we call survey mode. When I'm doing survey mode, I'm basically pulling out a pattern and having to index it right away. So in survey mode, I go ahead and pull out the pattern, see what's indexing it. And I can start playing with my pattern quality there. Okay, move it down, re-index it. Okay, my pattern quality is going down. Am I still indexing that same grain consistently? Yes, I am. Maybe I'll take a very, very small map on an area, go, okay, am I getting consistent data for each one of my grains? Then I can go ahead and move on. The other question I have is, does this affect confidence index? Usually it's going to have a little bit of change in your confidence index because of the poorer quality patterns. You'll have a little bit more of basically a broadening of your results, so the voting will get a little bit more open, so to speak. You'll have more choices because of a little bit of the give, because the lines are not quite found as quite as accurate. But that change isn't really a big difference, and you can see that when you start doing things like cleanup, that your grains are consistent. Confidence index is one of those tricky things that honestly deserves probably its own webinar just by itself. Another question that says here is, we only really see what the camera shows. Is there any way to know what the data quality will be before taking scans on a sample? And again, that's where I would use survey mode. Survey mode would let me basically take a quick point, look at the results, and see if I'm consistently getting relatively high CI and a good fit for the data that I need. And then I can say, okay, let me run a map. The nice thing about this is, again, if I'm pushing for speed, I can take a map like this in 2 minutes and move on. Versus where previously it might take me 10 or 15 or maybe even an hour or 2 hours, depending on what I'm doing. And now that I have this ability to really start pushing my camera and getting that high speed, that's right there is what I'm going for. I no longer have to worry about making sure everything is absolutely perfect before I do a scan, because it only takes me minutes to do a new scan. Why before, if I'm really kind of working slow, I need to think about that. Go ahead and move on to the next slide. So one of the ways you can also do this is what we call frame averaging. Now, the issue with frame averaging is that the reason I'm showing this will become apparent in a minute. With frame averaging, I can improve my signal to noise, but I'm going to start killing my total time spent, because I'm looking at taking multiple exposures at multiple spots, and I'm going to start lowering this. Now, we've recently added a way of getting around this, which we call native pattern averaging and re-indexing. Essentially what this does is it lets you take worse patterns and get, again, same quality results by averaging around it. So in this case here, we use a hex system. I'll talk a little bit more about that in a bit. And what we're looking at here is I have my pattern in the middle where my beam is. I can take the 6 nearest neighbors, average them together, and get basically a better quality by increasing my signal to noise, by also maintaining the acquisition speeds. Because if I go back and look at what frame averaging does, if I basically average 2 frames together, I've doubled my acquisition time. And while I'm getting good quality patterns, again, I'm pushing for speed. Something like NPAR lets me go ahead and get that speed I need, and also get high quality signal to noise patterns. This right here is a map that we took without NPAR and with NPAR. We've seen here we have an 11% indexing rate on the left. You can see that it looks relatively noisy. While you run it through NPAR, you get a relatively good map with 96% indexing. And if I ran this through cleanup following this, this would be a perfectly usable map for whatever I wanted to do. Quick question I just got, will NPAR work on a square collection grid? It does. There are multiple reasons we don't like a square collection grid, and I'll talk about that at the end. A hex grid is better for most work for multiple reasons. Here we can see again that NPAR in general does a very good job of cleaning up noisy data. Now the thing to remember is that NPAR is a post-processing thing, and post-processing basically means my data acquisition is not I'm not worried about time of data acquisition. So I'm doing this after I acquire my data. I have there's a relatively large group of university people on here today. A lot of them are students. you're paying for your scope time. And if you're doing that consistently, you're $200 to $300 a day. Well, I want to start pushing the speed, and I can push that speed even further with NPAR. So here again is an example of this data. We can see the effects of the EBS patterns on this. Again, we actually started increasing our gain to start playing with this. And the case you can see here is that look at these patterns. This right here is the power of the Hough, and this is kind of the big point here. Even ignore this as NPAR. Just look at the data. Let me go ahead and kind of explain a little bit more what we're seeing here. On the left, we have the patterns themselves. With the patterns themselves, you can see we have A, B, C, and D. We're increasing our gain, we're lowering our pattern quality. The first sets of maps in the middle row are just the raw data. And what I can see with that raw data, without running it through NPAR, is that I am still getting a lot of high consistency data, even with high noise. Look at the difference between A and C and the pattern visually. Visually there is nothing that you can really see for the lines, but the computer is still consistently doing the Hough and indexing the Hough and working on that. And then you run through NPAR, the data gets even better. So that's kind of the whole thing here. That's really is the thing that I want to push out to you guys. If you take anything home from this discussion today, realize that the Hough is an extremely powerful tool, and because of the strength of this tool, the pattern quality you really need for good data is much lower than you think. Starting to get a lot of questions about NPAR, and I'm going to move on a little bit to talk about background subtraction. If I have time, I'll answer the questions on NPAR, and if I don't, I will get them an email. So again, here's kind of our recommendations. For standard mapping, you do 8x8 binning on the DigiView or 5x5 binning on the Hikari. Often I usually do 8x8 even on the Hikari, sometimes even 10x10. And when I do this, I'm going to start pushing my frame rates up into not just 200 patterns per second, but 400 to 600 patterns per second. And on good samples, like by good samples, I mean like nickel and things like that, I can really start pushing it over 1,000 relatively easily. For simultaneous EBSD and EDS work, which we haven't really talked on that much, but just double check your EDS count rate to make sure you're getting enough EDS data. If you're really starting to push your speed at this level, your counts per pixel for EDS can often be a little bit lower than you would like. So if you're doing that, you need to think about, again, what's my purpose of my data? If I do need an EDS data with my EBSD, I need to slow my camera down to make sure that I'm getting enough EDS counts. Again, for phase ID, I'm going to use 2x2 binning and 1x1 binning on the Hikari because I need those high resolution patterns. If I don't have those high resolution patterns, I'm kind of going around what I need to do. That's mainly the basics of our camera settings, and I want to talk a little bit about backgrounds and how to use different backgrounds because, again, it's something I often see is people sometimes using the wrong background for different things. So the background is essentially a way of looking at getting rid of some of the artifacts of our data collection process. So what the background does overall is it increases the contrast level, smooths the inherent intensity gradient, and helps improve band detection because of those previous two. The big thing to realize here is that here's an example on the left without background and with background on the right. There's a huge difference in contrast between these two. And part of that contrast difference is because of the inherent intensity gradient. The reason for this intensity gradient is actually you have to start thinking about how your signal is propagating through space. So my signal is essentially coming from a point source on the surface of my sample. My sample is tilted. So as I propagate out in space, my wavefront is basically going out as a sphere. So what's going to happen is it's going to hit the pattern center first, and that's going to be maximum intensity. As it propagates out of that sphere, that intensity is lost at each pixel, and that's what the intensity gradient you're seeing on this is. Another way I like of explaining this is, let's say I was throwing a ball at a wall. If I was throwing a ball at a wall and I threw it, there's going to be a spot that hits first, and that's going to be a lot of energy at that spot. As the ball continues basically smooshing into the wall, more of that energy is going to be absorbed over a larger area, and because of that, there's basically an energy gradient. It's the same thing as going on with your patterns. It's the spot is diffracting, it's going out as a sphere, and there's going to be a spot on your camera where it's going to be the highest intensity, and we want to get rid of that. Now, what I want to make sure is when I'm doing this background, I want to make sure that I'm taking what's appropriate. And what I usually want to make sure is that there's a large number of grains covering the area. Now, when I'm doing a background, I usually zoom out by about a factor of 4 to make sure that I have a large enough amount of grains. I want to make sure that essentially I'm not taking a background on one single grain, and then that background signal now becomes my actual pattern that I'm seeing. That's the danger of doing large grain specimens and taking a background at the wrong magnification. So when I do that, again, I usually zoom out by about a factor of 4. If you're using the optimization routines, they will automatically zoom you out by that factor of 4 to account for that. There is a danger with the optimization routines in taking a background if you're near the edge of your sample. If you're near the edge of your sample, you zoom out. Your camera is basically be looking at free space now, and because you do that, that free space is going to mess up the intensity gradient. So be spatially aware of where your sample is. And that's why whenever I'm doing any sample, we have cell phones. Everybody has a camera in their pocket nowadays. Take a photo of your sample before you put it in so you know where you are on your sample and if I need to be aware of maybe going off the edge. So the magnification I'm going to be doing this work at, though, should be dependent on the grain size of my material. Again, I just want to make sure I have enough grains that one grain is not being the main part of the background. There should not be a latent pattern on my camera when it's basically rastering over it. And this right here is kind of what this shows. So for this material here, we had about 40 microns for the average grain size. Imaging at about 120x produces no latent pattern on the camera itself. Again, that's what I want. There shouldn't be any latent pattern up here. If you're doing this, you might see a little bit of flickering on your camera. That's basically it rastering over it, and that's what you want. You want this to be a little bit of flickering because of that. The other thing to make sure is that making sure your raster is at a fast rate, preferably TV rate, again, to avoid any latent EBSD patterns. If I'm going over my image slowly and I take a background, I'll basically only do background on part of my image instead of my whole image. That's why I want a fast raster. So fast raster on an area and make sure I'm not going off the edge. How do I capture the background? There's a couple of different ways to do this. We have both what's called the smart background and the SEM background. They do essentially the same things, but in different ways. The smart background in here is what actually zooms you out by that factor of 4, takes the background and puts your magnification back where it was. The standard background, the SEM background, just does the area that the SEM is currently at. Again, our systems can basically have full control of most of the settings for the SEM. In this case, the magnification is one of them. Zoom out, take a background, put your back in the smart background. Anytime you do one of the optimized routines, it'll always do a smart background. Be aware of that, again, if you're near the edge of the sample. I just got again a question about saying what should I do or magnification. It depends on my grain size. I need to make sure that I have enough grains and I'm not seeing a latent pattern. I just can't say, hey, do 125x. Again, it's going to depend on your material itself. Now, the way of actually applying the background is here is the image processing tab. The standard one is going to apply a background and a couple other things. I usually tell people to go in here, change this to custom mode, and start playing around with it to see our different image processing. That's a whole lecture by itself, too. To apply the background here, we can see it. This is our standard one. And we can see that the static background is already there with the histogram normalization. This gives us better contrast on our image. Again, this is our standard one. Our other common background is to be called a dynamic background. And this background is important to use for some different samples. The reason you want to do this is a couple of different things. The dynamic background is basically a blurring filter, and this is best on either extremely large grain samples or for single crystals. Also, sometimes it works on rough surfaces, but we usually don't want rough surfaces because, again, there's other issues with rough surfaces EBSD. So dynamic background, single crystals, and extremely large. And to do that, you have to go down here to the image processing mode, go to custom, and do dynamic background. Also, dynamic background is being used more and more with Atom Probe Assist, but I see the list of people here. I don't think we have any Atom Probe users here. Again, if you do, I can actually kind of tell you a good recipe to use for dynamic background, but again, I know most of the Atom Probe users. Again, here's just kind of the quality of the patterns with the filter passes for the blur patterns, but do remember that if you are doing this, that the blur filter, if you start adding more and more passes to it, you're doing a time penalty. I see a very good question here is, does the order matter between background subtraction than intensity normalizations? It does. You usually want to do the dynamic background subtractions and those kind of things first because you'll see a very, very large difference between them. This is something you can play with, and actually kind of works well with this next kind of slides here. This right here is our image processing custom tab where you can control what the background does. Left side, you'll see a list of basically functions that you can do, and those functions are, again, order dependent. So on this case, what I would do is, in this case, dynamic background subtraction, click a little arrow here in the middle, and it would add it to my recipe on the right. You can also see below there's two little arrows, one up and one down button. These up and down buttons change the order of these. In the next slide here, we'll see kind of what's going on here. So in an image processing tab, again, my static background, and then I have my intensity stretch. Now, if I change the order of these, what would happen in this case is it usually blurs it out to make it almost completely white. So again, the order matters. So the stretch really helps us increase the brightness and the contrast of our pattern to help us along the way. This is computationally really easy to do, so there's really no time penalty for doing this. But if you are doing things like the dynamic background subtraction or division, you start to add a little bit of a time penalty because each one is now going to doing this. So again, here's the routines, and you can really kind of make a customized list of that. So this is the big thing. Again, we're looking at the image processing. This is something I would tell you guys to sit down and play with, and again, see how the order changes. See how things like the normalization and the stretch change my pattern quality and contrast, and see how it works with the indexing, because this is going to be one of those things, again, you can start playing with to not really gain or lose time, but get better band detection. Because remember, in the end, what we're really looking at for is, can my Hough still find my lines? So this is a good slide to kind of go over a lot of things. So if the biggest issues you're going to see is that the bands do not match an actual band. What we can use to do with that is something called changing the row fraction. The row fraction is a slider on the bottom right side, and this basically brings the pattern in. So we see the circle here, see the ring. This is the row fraction. If I lower the row fraction, it brings the ring in. What often happens is that you'll have an artifact of something like on the camera or on the edge of your sample, and that artifact will be picking up as a line. And that line, again, is fake in this case. It's not an actual crystal line. So if I bring the row fraction in, the Hough will no longer find that as a line. The other thing to make sure is that we have our Hough bands here. If they're wider than the area being detected, then I want to change my mask. So you can see my mask here is currently a 9 by 9. So if my bands are wider than that, I want to open up my mask. If they're smaller than that, then I want to close my mask to a 5 by 5. This is to make sure that my band width is correct. So this is going to be the main settings you're dealing with. The other thing I usually do with the Hough is I deal with the vertical bias. The vertical bias is very, very sensitive. I usually take it to 1, 2, or 3. And what that will do is essentially move what the Hough space here on the left, the square area, it'll make sure that I'm getting away from the bottom, choosing more toward the top. Again, it's extremely, extremely sensitive. Got a question about the row fraction. Which direction should I move it? You usually want to move it down. I usually keep the row fraction about 85% because then I know I'm not getting any artifacts on the outside. That's the big thing here. We want to make sure that there's no artifacts. And if you usually see artifacts, they're going to be on the bottom of the Hough. They often look like big, like Nike swooshes, so to speak. So those are something to keep in mind. That's when you want to bring the row fraction in. And another question, and talking about speed, is going to be the step size selection. The step size selection is one of those things that you're going to have to learn over time of how to use it. What we typically find is that take your grain size, divide it by 10, and you usually get enough resolution that you need. The thing to realize here is that your step size, if you lower the step size, you're going to start paying a gigantic, gigantic time penalty. And here kind of shows that. In the top left, I have 8 micron steps. They will take the entire map in 2.5 minutes. If I go to 4 steps, 4 micron step size, I've now taken essentially 4 times the amount of collection time. I go all the way up to 1 micron steps. I'm now at 2.5 hours for an entire map. Because of this, remember, if I'm essentially, anytime I double or cut in half my step size, I'm actually doing it by a factor of 4 how many pixels I'm doing. So we can see that each step, 8 to 4 to 2 to 1, is causing a very, very large increase very quickly in my size of my map and my collection time overall. So something to think about here. Again, it's what am I doing also? We can see that the map data is relatively consistent. I start to get a little bit more jagged edges on 8 microns, but do I need that kind of data for what I'm doing? Down here at 1 microns, I can see all these twin boundaries good. All my boundaries are relatively nice and straight. And the other thing to keep in mind here, which I said I would talk about, is the hex grid system. Again, in traditional SEM imaging and EDS mapping, people use a square. The issue here is that in a square grid is not optimal for EBSD work because it does not provide constant point-to-point distributions between your center points. So if I'm looking at grain boundaries and things like that, I'm always going to have basically an artifact based on the square grid because of that. And those artifacts, especially looking at grain shapes and statistical analysis, are big. And what the whole thing here is that the hex grid is equidistant all the time between every square pixel, between neighboring pixels, excuse me. So here I have 6 neighboring pixels, and between each pixel, I have equidistant points. That's the key of the thing. And because of this, I can basically look at smaller things. So this is the advanced reasons of why we should use the hex grid system. Kind of slowly wrapping it up here, we do have additional resources available on our website. We of course have a blog at edaxblog.com where we kind of keep you up to date on some of our newest news. We also have movies on a lot of the things I talked about, shorter movies for things like NPAR at YouTube at users at edax-news. And of course our webinars, which you probably already found, are at edax.com/events. The webinars are very useful tools. Going back, I think we have 5 or 6 years now of webinars online that you can go back and look for. So all this information is available for you guys always on the website. Now I'm going to start going through some questions here. The first question here is, does the EDAX camera have hexagonal pixels? No, our cameras are square pixels. The question is the hex grid is your scanning parameters. You're scanning in a hex grid instead of a square grid. So it's not controlled by that. And what the camera sees doesn't matter. It's basically where I'm putting my data on my map itself. Let's keep going through questions here. Okay. We have kept up with most of these questions. There's a question here about what's the total time for a sample for better definition of dual phase steels. This is not a straightforward question. It's an issue of, there's a whole bunch going on here. It's how do I figure out which phase is basically better in dual phase steels. Again, when you're doing something like this, you want to make sure that you're I usually do this in survey mode first. I would go ahead and do survey mode, make sure that I'm getting questions make sure that I'm getting data that answers the question I'm asking for. So I go to a phase that I'll know it's a phase, make sure that I'm consistently indexing it, and then either increase or lower my gain, make sure my Hough parameters are going, and then start doing an actual map. A lot of the other questions are relatively high-level questions right now. So I see a question here about minimum magnification for EBSD. There is no real minimum magnification. You can do this at what you want. You need to make sure that your step size and your background are key. The person also had a little bit more information. I'll go ahead and email you something else on that. Missed a comment. So another question here is a question about the factor of 4. When I was talking about the factor of 4, I was talking about the smart background. The smart background zooms out by a factor of 4 to basically make sure we're getting enough crystals to making sure that our background doesn't have any latent thing. So that is factor 4 is based on that, not on grain size. And then what else do we have? Is NPAR a separate software needed to be purchased? NPAR is a license feature that you'd have to talk to your sales guy about getting. Which means to me there should be some older NPAR. Is NPAR applied using the analysis software? NPAR is actually part of both team, and I can now believe I can answer this, is that we're actually added NPAR to our next version of OIM 8. It's in our latest newsletter and insight, and also we'll be announcing more details at M&M. Answers this question too about NPAR functional data collection. NPAR is not a data collection routine. NPAR is a data post-processing routine. So it doesn't really do anything purely with the patterns until after the entirety of the data is currently collected. It's also proprietary, so you won't be able to get that from our competitors at this point. A couple questions about TEBSD. I'll cover those in emails. I think most of the questions right now are more pointing towards, actually a very good question here. Is there a relationship between beam spot size and grain size? And the answer is kind of. The beam spot size is one of those tricky things that kind of depends on what's going on with your scope vendor. The beam spot size and what it truly is one of those fuzzy things that kind of goes on. Now, what you're really looking for in EBSD is your interaction volume. And your interaction volume in EBSD is relatively small. So you usually don't have too many issues of artifacts in your data based on spot sizing and the beam spot size and the grain size. Usually. It's not quite that straightforward depending on what's going on. Also, you have a lot of high angle grain boundaries. You can also have an issue where you get overlapping patterns. And the nice thing is that our voting method actually does a really good job of deconvolving patterns, but that's not the topic of this talk. So this time, there actually are quite a few unanswered questions. I will get around to answering those hopefully in the next couple days, maybe the early part of next week. So thank you guys all for your questions. And at this time, I'll go ahead and sign off. Again, I'll get to these questions, and then I'll look forward to talking with all you guys. I hope I kind of explained what's going on with the camera acquisition settings, and you can go ahead and start using this information you learned today to get a little bit better information off your system. So, thank you guys.